Okay, so this is my first time actually giving a lecture out with a mic, so it sounds really weird, but... So, thanks Itai, thanks Ron. I hope you enjoyed their lecture and that you stayed awake. And now we're going to go and talk about something interesting, which is Spark-Kafka and managing offsets, or how we started to actually enjoy offset management. First of all, this is Kafka, and just a fun fact, he was terrified of mice. So, you know, you learn something new every day. Now, I'm going to talk about 4 things in this lecture. The first thing is going to be how we used to work. Then we're going to talk about what we wanted to do, and even more importantly, why. Then we'll go into what we actually ended up doing, and I'll walk you through the solution and the design and thought process behind it. And then, for everyone who'll stay, we'll go into extra benefits, which are always fun.
Includes beer or not?
Oh, what?
Include beer?
Yeah, of course, beer is an extra benefit. Yeah. Yeah, there was supposed to be beer. I hope there's still some. Okay. So, first of all, who am I? So, I'm Simona, I'm 26 years old. I'm working as a big data engineer here at the NSC. I love data. What's not written on this board is that I've been dealing with data, both structured and unstructured, for the past 8 years now. I love music, the weirder the better. I go to tons of concerts, and I love Japan. So, this is me in Japan, so this is me in a picture. Great. So let's move to how we used to work. And Itai and Ron talked about this in their presentation, so what we're going to do is just name the teams Team Ron and Team Itai. So, Team Ron, let's look at the differences, which are very, very important for this lecture. So Team Ron used to work with 4 to 6 minute long micro batches, which is actually micro, right? And Team Itai used to work with 1 hour long micro batches. And we thought that's completely fine. That's like micro for us. Then the second difference comes to the output that we commit at the end of each micro batch. So while both Team Ron and Team Itai committed Kafka offsets, right? They committed them through the brokers, would send a request to the Kafka brokers, okay, and commit the offsets through them. Team Itai also committed file names. So they committed file names to a Postgres database under an RDS service in Amazon. We thought these differences didn't mean a lot. And the reason for these differences between the teams is just business logic. Now, the way we used to define starting offsets is the way you tell Kafka from which offsets to actually start at the beginning of your application, is in 4 different ways. So, first way is Kafka Offset Manager, and I'll talk about it just in the next slide. Then we have earliest and latest, which are very basic, right? If I specify earliest, I'm going to read from the beginning of the topic. If I specify latest, I'm going to read from the end of the topic. And then we have XML. And XML is a very interesting option. So when would we use XML? What is XML? I guess all of you know what an XML file is, right? So we use XML to specify very specific offsets that we want to start from. When would we do that? When would we need such a thing? Well, in case of disaster, in case that we didn't process data correctly for a few hours or for a few days, we want to start processing from very specific offsets, from the last commit point that we know that was okay. So in emergency mode, we start constructing an XML file, right? So we have to provide for each partition for this topic the offset to start from. And an XML file looks like this. So it's a very long, error-prone process, and we did not enjoy that at all.
How many partitions?
So some of our topics have more than 500 partitions. We'd write scripts to do that, but still, it's very, very stressful. And then you upload the file to S3, restart your application, and hope to God everything's okay.
Why not override the
Yeah, because let's talk about how the Kafka Offset Manager works. So the Kafka Offset Manager is a solution that we wrote in-house. It's our solution written by us, Scala, so self-made. What it does in the beginning, when the up just goes up, it retrieves offsets from Kafka and provides them to Spark. At the end of each microbatch, it commits offsets through the brokers. As I already said, we thought there was no problem with it. We've been working with it for like 3 years now. But then we actually wanted to do something. So we wanted to do an upgrade. So before I go into this section, does anyone have any questions? Okay. Oh yeah.
So you committed the offset to the end of the batch, and then when you start it again, do you read it, or
No, I don't need to read it. So in case this wasn't clear, we're talking about Spark streaming applications. So Spark, you don't need to provide to Spark at the end of each microbatch or in the beginning of each microbatch the offsets for Kafka. Spark just manages it on its own. But you do need to provide them at the beginning of the application when you just create the consumer.
So when you start, you can tell him read from this
Yeah.
topic or whatever topic.
Yeah, exactly. Okay, great. So what we wanted to do is just a simple upgrade. We had our Spark-Kafka consumers version 0.8. We wanted to upgrade them to 0.10. But what's even more important is why we wanted to do that. So we have two main reasons. A is fairly simple. There was already Kafka 1.0 major release out there, and we're kind of falling behind, right, with the Spark-Kafka 0.8 consumer. And there were a lot of new options that the new consumer provided to us. I mean, in the Spark-Kafka consumer 0.10, when you add new partitions to a topic, you don't actually need to restart your application. Now it sounds like, yeah, of course, but in 0.8, every time we add new partitions to a topic, we have to restart our applications and provide Spark with the number of partitions that topic had. The second reason that we wanted a change with our infrastructure is the fact that, as you remember, TinyTie has two outputs to commit. They have the offsets, but they also have the file names. And since they're both being committed to different resources, one to Kafka, the second one to Postgres database, they're not entirely consistent. I mean, in case we write offsets to Kafka successfully, but then don't write the file names, we're in a problem, we're losing data. In case we're committing the file names, but not committing to Kafka, we'll get duplicate data. And that's a big problem for us. Data consistency is very, very important. So, in that in mind, we looked at the differences between the two consumers, and I'll just mention them briefly because the lecture is not about that. But the Spark-Kafka consumer has an entirely new Spark-Kafka consumer API 0.10. From even the object that you get back from the consumer is new. So consumer record. The second thing, there are tons of new consumer configurations, a few of which are timeout configurations, which we thought nothing about. And then, last but not least, the way you subscribe to Kafka is different as well. So the option that actually provides you with the benefit of just seamlessly adding new partitions to a topic is the consumer strategy is subscribe, right? So that's also a good thing that we got only in the 0.10 version. Now, Team Ron did the upgrade first, and they encountered some problems, right? The Kafka concurrent modification exception, that was one. They encountered some problems with restarting the applications, but they were done, right? Their consumers were running in production. So TinyTie, the guys with the 1 hour long microbatches, they thought, okay, we can do that, right? Like, we'll just write all the code in like 1 week, and then we'll run it in the dev environment for a few days, and then production, right? Like, sounds really easy, no problem, no. So we wrote all the code, and then we started getting problems. So the first problem we got was while actually committing the offsets at the end of the microbatch to Kafka. And you may ask yourselves, why? Why would you get a timeout? You didn't used to get timeouts. So we asked ourselves the same thing. Now the thing is like this. So let's look at the time we actually have a consumer that is working against Kafka. So we have a 1 hour long microbatch. let's say for the first 4 or 5 minutes, we're reading from Kafka, right? What do we do next? We process the data for like half an hour, even 30 minutes, and then at this point, we write the file names and we commit the offsets. So by the time we actually try and commit the offsets against the brokers, our consumer is way long gone, long disconnected. And in case your consumer is not actually connected to Kafka, you can't commit the offsets through the brokers. So we said, okay, no problem at all. So our timeout is too short, right? Our microbatch is 1 hour long, so let's make our timeout 1 hour long. You know what? No, let's have a buffer. Let's make it 1.5 hours long. So we did that, and we were fine. We actually managed to commit our offsets against Kafka, so our consumer was still connected. And then we had a configuration problem. So we decided to restart our consumer. And then suddenly we couldn't connect to Kafka anymore in startup. Why is that? Because the timeout was that long and the consumer was actually still connected to Kafka. So Spark would wait until the old consumer would be disconnected from Kafka, and only then would it reconnect. So this can take up to 1.5 hours just to restart your application. This does not sound okay. But now we're in a problem, okay? The timeout is actually too long, right? But we can make it shorter, because if we make it shorter, we go back to square one. So we said, okay, maybe the problem is our shutdown process. Maybe we have a different way of like disconnecting our consumer. Maybe we're not doing it right. So we decided to use a Spark graceful shutdown, because before we just gave sigtem to Spark, right? So what Spark graceful shutdown does, it goes like element through Spark and shuts them all down, waits for everything to finish, and then goes down. But our microbatches are 1 hour long, and when you actually perform a Spark graceful shutdown, the job generator is still running. It's still generating microbatches. The microbatches are not going to be executed because Spark in the shutdown process, but it's still generating them because data is still coming into Kafka. So what would happen at this point is that we have to wait up to 3 hours to get our application down, just to wait for Spark to finish. So we said, okay, maybe our entire working process is wrong. Maybe, just maybe, we shouldn't be using our Kafka, our Spark offset manager. So, okay, is there another way to commit to Kafka? So the offsets, yes there is. We can use Spark, we can use the Spark API. So the Spark-Kafka async commit. For those of you who are not familiar with the Spark-Kafka async commit, what it does is when you request a commit, Spark would actually just take a request, add it into an internal queue, and then at the beginning of the next microbatch, it would pull the queue, say, okay, there's a commit request. I'm going to commit the offsets to Kafka now. Where is the problem with that? Well, actually, the commit request happens just before Spark opens the consumer. So what would happen now is, because we shortened our timeout again, we would again get a timeout because our consumer was no longer connected to Kafka. So at this point, we were at a complete and total loss. And then we came up with a final solution that actually helped us. The terminology was wrong, but okay. So what did we end up doing? We just designed an entirely new solution to manage our offsets in RDS. That means in Postgres as an offset store. Now, this may sound familiar to you. Why? Because Timitai is also saving their file names at Postgres. So these are the topics I'm going to talk about our solution. Are there any questions up until now? Yeah?
On your Spark streaming job, besides managing your offset by yourself to whatever Postgres or database you're using, do you use checkpoint for crashes? Or do you manage
The question?
Yeah, sure. So the question that was asked was, do we use checkpoints? I believe that we don't use checkpointing. We just manage our offsets, but we're like completely fine with that, because as long as we terminate the application or the application crashes mid-batch, we don't care. And the reason why we don't care is because right now we have consistent committing, which I'll go into a bit later.
If you check the zookeeper for consistency of the offsets?
We used to use Zookeeper before, but I think that regardless of offset committing, we believe that the advantage this solution gives to us, because we also commit file names, it gives us a bigger advantage. I'll also go into that when I talk about consistent committing. Okay, so first of all, let's talk about our offset store, our design. So Postgres is RDBMS, structured data, right? So let's just look into the table so you guys will understand a bit better. So this is just a snippet from the offset store. And what is important to understand, this triplet, so consumer topic partition, is our unique key, right? So for each consumer name, for each topic, for each partition, we save the latest offset. Another column that we have is the last updated column. Why do we save and how do we save the last updated column? We just have a trigger that's defined on the table. Every time that we save a new offset, okay, every time that we update a row or maybe insert a row, we just also save the system time. Why do we do that? Kafka's not using this information, right? But we might, right? So in case we actually have a problem with lagging or some sort of problem, this is just another control check that we can do. We can just log into PSSQL or whatever other SQL tool we're using and just check this column for the last updated time for the offset.
Excuse me?
Yes?
How long do, every each time, how long do you update the offset? That's the beginning?
At the end of each micro batch.
For example, 1 hour in the beginning and the end.
Right, so, right. I'll go into this topic more when I talk about consistent committing, because I think it's really, that's like the essence of that topic. Okay. So let's talk about how we subscribe to topics now. So I guess not all of you can see really well, but this is our method. The first thing that we have to do is just check if this consumer was ever started before, or more like, did it ever save offsets in our DS, right, in our Postgres table. So it's fairly simple. You can just query the table and check if there even one row that exists with a consumer that has this name. Now, if it doesn't have any offsets saved in the table, that does not mean that this consumer was never started before. It just means that it never committed the offsets into a table. But it might, this consumer might have been started before, just committed offsets to Kafka. So what we do, we just subscribe to Kafka without a topic map, without an offset map. And what this actually means is that if this consumer was started before, we're going to start from the offsets that were saved in Kafka. If it was never started before, we're just going to start from the latest offsets. So what we do after we retrieve and answer that question, if offsets were actually stored in Postgres, we have to build the offset map. What is the offset map? Well, it's a map object. It has a key of topic partition and value of long, which is actually our offset. So the first thing that we have to do to construct the offset map is to understand how many partitions does our Kafka topic have. The way we do that is fairly simple. The one that has this information is Kafka. So we just send a request with the Kafka API and say, hey Kafka, how many partitions does this topic have? And Kafka gives us back the answer. The moment we have the number of partitions, we need to retrieve the offsets that were saved in Postgres. So this SQL looks a little bit intimidating. It's really not. So what we'll do right now is I'll walk you through this SQL, and then in the end, you can ask as many questions as time allows, but hopefully you won't have any questions. Okay. So what we do here, we create a join between two tables. One of the tables is just a generated series from 0 to the number of partitions minus 1. Why minus 1? Because Kafka, as you all probably know, counts from 0 to n minus 1. Then we join this table with another table, which just represents the current offsets that were saved. What? Sorry. that were saved. Okay. Sorry. Itai, thank you. Okay. So we just joined this with another table, which is just the current offsets for this consumer. So we filter by consumer name and by topic name, since we need all the partitions. So what happens next is for each partition that already exists in the table, we just set the offset to the current offset. And for each partition that doesn't exist, we just set the offset to 0. We do that because our policy is if we didn't consume for this partition, we want to start consuming from the very beginning. Are there any questions? Cool, I did it. Just to visualize it so you'll get it even better. So here we just retrieve the offsets for a topic that has, let's say, 30 partitions, so we count from 0 to 29, and here we have all the offsets. Here, on the other hand, we have all the offsets up until partition 200, right? 199, and then we just have zeros. Then if you've ever worked with the result set in Scala, you know that it returns basically, you can get it as a vector of maps, which each map representing a row from a table, right? So each map has the partition and the offset. We have the topic as a constant basically because in our organization, our use case, we always consume from one single topic. So it's a constant, and then we just reduce all the rows and create our map that has the topic partition and the offset as a value. Okay, so for the hot topic, because I got a lot of questions about, the to-resource commit. So what is the to-resource commit? Why do we need it? And how do we end up implementing it? So why do we need that, which is the very important question. When I just started this lecture, I said that data consistency is very, very important to us. Right, and as I already mentioned several times, Team Itai outputs two sorts of resources. First of all, they output the offsets of Kafka, and then second of all, they output the file names. And we need both those resources to be consistent, because if they're not consistent and the committing is not consistent, we'll either get data loss or data duplication, which is very, very, very bad to us. Now, the final output, I mean, the output of the files and the output of the offsets, we get that only at the end of the micro batch. I don't care if my application crashes in the middle, I can just rerun that micro batch as long as both of them are committed and consistent.
How do you implement exactly once?
What?
How do you implement exactly once in the Kafka?
Okay, because our output, okay, in case that we did not commit the offsets and we did not commit the file names, our application will go down. Okay, we'll have to restart it because we had an actual problem in which we couldn't commit those resources against RDS.
Yeah, but it's
And then we'll start reading from the latest offsets that were previously committed. So we're going to read the old offsets since our micro batch didn't finish correctly.
But then you
will have duplication for several.
I won't have duplication. The reason that I won't have duplication is because my output doesn't only consist from the offsets. So I also have the file names. In case I didn't output the file names, the second part of the flow won't have anything to process. And because of that, if my micro batch crashes,
already moved it to the next. If you already moved to the next step, it will take the file name, go to the file and see it's not there. If you put it in.
I'm sorry, could you rephrase the question?
What you're saying is because you're using file names, and the other step is taking the file name and taking the file.
Yes.
After it finishes with the file name, it will still go to the file, but it won't find it on the
No, that's not what I'm saying. So the question was, what happens if the next step comes and tries to read the file, but the file is not there? The thing is, I'm committing both the offsets and the file names on the same connection. Okay? So it's either both of them there or both of them are not there. If the file names are there, the files were written to S3. Okay? Like 100% sure of that. The file names are written to the database only after the actual files were written to S3. But the files to process are set by the database.
Or you can reading the same.
Okay, if this is still unclear by the end, so we can just talk about it later, okay? Cool. So that was a spoiler. So the next question you should have is actually how do we implement it? And the reason for this question should be because we have two parts here, right? Committing offsets is being done in our infrastructure, right? And all the inserting process and everything, it's done in our infrastructure. On the other hand, writing the file names to the table is being done in the application. It has nothing to do to the infrastructure. So how did we ended up implementing the fact that they both have to be committed on the same connection? So this looks a little bit intimidating. We actually defined a method that's called commit resource that accepts a connection. So what I'll actually do is just show you an example from Team Itai's code. Still looks a little bit intimidating, but we'll manage. So what happens here is that the commit resource that was defined by us accepts a connection. And then what Team Itai does, it does all its application logic. They take this connection object, they perform all the inserts or all their database logic regarding the file names, and then they're done, right? So they don't open the connection, they don't close the connection, they don't commit the connection, they only perform the SQL. The next thing that we do is in our infrastructure. So in our infrastructure, we have a commit method, and that commit method knows to accept a commit resource object method. And then what happens is that we check. If we did receive that method, then we have to perform both SQL statements. And we have to commit both of them together. So what we do, we just perform both SQL statements. And then when both of them were successful, we commit the connection and then close it up.
On the same connection?
Yes, on the same connection object. We create the connection object, we pass it on to the method that we received, and then we commit the connection and close it up. In case we didn't manage to commit the connection, we throw it an exception and we want the application to terminate, because in case we didn't manage to commit the offsets, we don't want to go into a state of data duplication or data loss. Okay, time for extra benefits. So I hope all of you are awake. So first of all, our restart time, because we managed to shorten our timeout back. Our restart time is completely normal. We just turn the application down, then turn it off again, and everything's fine. The second point is monitoring. So we're actually still committing to Kafka. There are two reasons to that. So first being monitoring our DevOps teams and IT teams. When they monitor our consumers, they monitor them using Borrow, meaning they actually monitor through Kafka. And we wanted to do all these changes, all these infrastructure changes on our side. We didn't want any dependency or involvement from the IT teams and the DevOps teams. Second reason is for disaster recovery. So let's say that my team lead Yaniv wakes up this morning kind of funky, logs into Postgres and drops a table. I still have all the offsets stored in Kafka. I can retrieve them from there and just restore my table. But the real question all of you guys should be asking is, how do they do that? She just spent like 5 minutes talking about how problematic it was committing to Kafka and messy and timeouty. Well, as I told you over and over again, when we used to commit our offsets to Kafka, we did it through the brokers. And then we had a problem because our consumer was not connected. You can't commit offsets to a disconnected consumer. But there are actually more options of committing offsets to Kafka than just through the brokers. So another thing you can do is just open a consumer using Scala, just like a Kafka consumer, not Spark-Kafka, and then give that consumer the same consumer ID and commit the offsets to Kafka. So what we do right now is actually a two-step thing. So the first thing we do is just try that option. So we just assume that our consumer is already disconnected from Kafka, because that's what happens most of the time. So we just open a Scala consumer, give it the same consumer ID, we have the offsets, and we just commit the offsets to Kafka. If this fails, and if this fails with the exception that tells us But there's already a consumer with the same consumer ID. We just do it the old way. We just commit through the brokers. So basically we're covered from all sides. But our real source of truth is the database. Okay. So another benefit is our new offset strategies. So while earliest and latest stays the same, right? When we use earliest, we read from the beginning of the topic. When we use latest, we read from the end of the topic. Database, of course, replaced our Kafka offsets consumer. But you know what's missing? The XML option is missing. So now when we have a problem, we're like in disaster mode. We don't need to construct an XML file. We just go log into PSQL, go into the database, and just edit that specific offset that we want to, or the 10 offsets that we want to. So it's way easier, and it's more visualized and GUI. So last and not least, because of the way our big data group developed, we had Team Ron and Team Itai, and each of these teams, they just wrote their own infrastructure. So their whole own entire way of consuming from Kafka and configuring a Kafka consumer, and their own way of committing and what committing and the offsets committing to Kafka. Now, because we have our own BD Commons, which is a big data commons project, they only need to use two methods, okay? Create Kafka dstream and commit. They need to configure the infrastructure, but all the configuration, opening a consumer, closing a consumer, committing, whatever, everything is unified. Everything is in one place, and they don't have to do anything else. And with this, I'm done. So if anyone has any more questions, it would be a good time to ask them. You don't. Okay, so I'm done.